Hello everyone, welcome back. In this lecture, we shall see problem on heat transfer analysis over a flat plate for turbulent flow conditions. We shall check the problem details. This problem has been taken from Heat and Mass Transfer book, 2nd edition by Eunice Engel. Okay. The local atmospheric pressure is 83.4 kilopascal. Air at this pressure and 20 degrees Celsius flows with a velocity of 8 meter per second over a 1.5 by 6 meter flat plate, whose temperature is 140 degrees Celsius. We can see the image here. Air is flowing at 8 meter per second and 20 degrees Celsius temperature. The flat plate is at a temperature of 140 degrees Celsius. Now they are asking to determine the rate of heat transfer from the plate if the air flows parallel to option A 6 meter long side and option B 1.5 meter side. Okay. In this case, we shall do only the 6 meter long side because it will be a turbulent flow condition, and we shall check the theoretical results and compare with CFD output. Next, let us find out the properties of air at this condition. Here we have to find out the film temperature, which is nothing but average of airflow temperature and the surface temperature. So the film temperature TF is given by 20 plus 140 divided by 2, which is equal to 80 degrees Celsius. This will be the approximate temperature near the wall boundary. So we have to consider this temperature and find out the properties of air. Okay. The properties are listed here for this condition, that is 83.4 kilopascal and film temperature of 80 degrees Celsius. The thermal conductivity K is equal to 0.0296 watt per meter per Kelvin, and other parameters like density, specific heat at constant pressure, dynamic viscosity and kinematic viscosity are given. Okay. We have to find out the net heat transfer rate for this flow problem. To find out the net heat transfer rate, we have to calculate convective heat transfer coefficient, which will be calculated from Nusselt number. We can calculate the Nusselt number from the empirical relation, which is a function of Reynolds number and Prandtl number. Okay. First, let us calculate the Reynolds number. Reynolds number is given by rho VL by mu. We shall substitute the values. Solving this, we get Reynolds number is equal to 1.85 into 10 power 6. So this is greater than 1 into 10 power 6. Therefore, the flow is turbulent. Okay. Next, we shall calculate Prandtl number. Prandtl number is equal to mu Cp by K. We shall substitute the values. So finally, Prandtl number is equal to 0.733. Okay. So using Reynolds number and Prandtl number, we shall calculate Nusselt number. Since the flow is turbulent, we have to use the formula for Nusselt number, which corresponds to turbulent flow. The local Nusselt number for turbulent flow at a particular distance x is given by 0.0296 Reynolds number raised to power 4 by 5 into Prandtl number raised to power 1 by 3. But this is at a local distance x. If you want to find out the average Nusselt number over the entire length of the plate, which includes laminar plus turbulent, then the average Nusselt number is given as 0.037 into Reynolds number power 4 by 5 or 0.8 minus 871 into Prandtl number power 1 by 3. We have got Reynolds number and Prandtl number. Let us substitute. The average Nusselt number is equal to 3418.6. Okay. Next, we shall use this Nusselt number to find out the convective heat transfer coefficient H. Okay. We know that Nusselt number is equal to HL by K. Therefore, H will be equal to K by L into Nusselt number. This is the average Nusselt number over the entire plate. We shall substitute the value of K, L and Nusselt number. Therefore, H will be equal to 16.86 watt per meter square per Celsius or per Kelvin. Okay. We know that Q is equal to H into A into Ts minus T infinity. We shall substitute the values. H is 16.86, A is nothing but 6 into 1.5 and Ts is 140, T infinity is 20 degrees Celsius. Therefore, the net heat transfer rate from the plate to the fluid is 18214 watt. Okay. This is the value which we have got from theoretical calculation. Next, we shall solve the same problem in Ansys CFX and compare the results with theoretical calculation. Next, let us open Ansys CFX.